Here's a quick review of op amps. You probably visited op amps a little bit in your circuits for non-ECE majors course. But you know, it's an elusive kind of concept, but I think it's important enough to cover because if you do get involved with a control system that has some external circuitry, chances are there could be op amps involved. So you should know a little bit about them and how to do some basic calculations with op amps. Okay, so one of the things I need you to know is in the past few examples that we've done, we called those passive circuits because they just had R's and L's and C's, and the elements themselves in the circuits, besides the power sources that were included, did not have any way of generating power. An op amp is different. Inside the little triangle symbol here, you can visualize that there's actually another circuit that has quite a bit of sophisticated electronics inside of it, including transistors. And so to make all this work, you have to have an external power source so that the op amp will work properly. So I've got that shown here with a VCC, anywhere, maybe it's 10 volts or 15 volts. You get to some flexibility on choosing that. And then a lot of operational amplifiers need a negative power supply as well, in the negative direction, minus VCC. That's so the signal can swing both positive and negatively. Okay. The main things you need to know to get to where you can do some calculations with an op amp circuit are the ideal assumptions. The gain of this circuit between the input terminals is really large. Okay, so if you put a very small voltage between here and here, it would produce a really large voltage on the output. In fact, it would drive it up to the rails of the power supply. And so what happens is that you can think of an op amp circuit as one that has feedback also, and it drives that input difference between V minus, let's call this point V minus, and V plus to be essentially zero, where V minus is equal to V plus. Okay, so that's one of the main assumptions that we make with an op amp so that you can do some calculations with an ideal op amp. Okay, the other thing that we do is we assume that the input currents coming into the triangle part that's representing this op amp circuit, it's got high impedance, and so it effectively blocks any current coming in, so the input currents here are assumed to be zero. Okay, with those assumptions, you can actually get to where you can analyze an op amp circuit relatively easily by just looking at the proper set of node voltages. Okay, one of the things that we don't know is the output current coming back into the op amp, or out of the op amp, whichever way you want to call it. But we don't know this current, so we can never write a node equation at this point because we simply don't know that current coming in there. All right, so let's give an example. All right, here's a node, and we can look at the current coming out of the node here and here and here. Okay, well, for this one's easy. It's zero coming in here. All right, so I'm going to call this I1 and I2. All right, so if you looked at I1, change it back to blue. All right, you can get the an idea of the current, but first, if you choose this as the reference voltage, okay, so back to red here. If this is 0 volts, then the plus terminal here is at 0, which means this point is also at 0 volts. All right, so those are the key assumptions, and once you have that, it's pretty easy to calculate these currents. All right, so I1 would be, okay, if it's moving this way, it would be 0 minus VI, because this point is at, with respect to the reference node, this point is at VI. So 0 minus VI divided by R, okay, is that current coming out of the node I1. All right, then for I2, that would be 0 minus V out, because that's the voltage difference across this resistor. This point here is, you can see it's tied to V out. All right, so there's V out. And this point is still 0. So 0 minus V out divided by RF is current I2. And since that input current into the op amp is 0, that does it with the equation. All right, so we can solve and get essentially a transfer function here where we'd have V out is equal to, and we solve, and we get minus RF over R times V in. All right, so our transfer function in this case, if we did it in the Laplace domain, everything's a constant, so it's still just RF over R, okay? And so there's no S's is my point that shows up in the expression. Okay, so this is an operational amplifier. It would be an amplifier if RF is bigger than R, meaning that any input would get amplified. And the minus sign means it gets flipped back to the negative axis, right? So if I had something that was input that looked like this into the op amp, when I flip it, it's going to go negative. Have the same shape. It's supposed to be the same shape, only negative. Okay, you get the idea. All right. So that's the first part of my introduction to op amps. I'll do another video here that shows a few more calculations.